For example number 2, we have compute the volume of a solid. So we know this is going to involve a volume problem, just like the last example, whose base is bounded by the curves f of x equals x squared and g of x equals 4. So same as example 1 as far as the graphs go, but let's keep reading. With horizontal, so this time our cross sections are going to go this way and not this way. They're going to be equilateral triangle cross sections, and they're going to be perpendicular to the y-axis, not the x-axis. So again, same graphs, however, the cross sections are going to be different, and that's why I'm going to follow the same steps. Step 1, we need to draw this on top of the Cartesian plane so we can see exactly what we're looking at. Here are our two graphs, g of x equals 4 and f of x equals x squared. However, if you go back and read the problem, it says it needs to be perpendicular to the y-axis. And those cross sections are going to be horizontal. So that means our cross sections are going to be going this way. Therefore, they will be perpendicular to the y-axis, whereas in the last example, they went this way. So well, we want to sketch all of this stuff. Step 2, like we did before, draw a bird's eye view of the three-dimensional shape on the plane. So bird's eye view means you're looking at the top of the three-dimensional shape. This would be the base of the shape. And basically what that means is you're just graphing the two functions. We can see that they intersect here at -2 and 2, just like our last example. Step 3, draw the shape of the perpendicular cross sections. Well, again, it says that they are equilateral triangles. So for step number 3, I'm just going to draw shape. Might even make it a different color just for it to stand out. But these equilateral triangle cross sections are going to be popping out of our graph. Okay? And again, they're going to be going this way. So that leads us to step 4. Sketch the lines of intersection of the cross sections on the Cartesian plane. So here we have the base of our object, and our equilateral cross sections are going to be perpendicular to the y-axis, and therefore they're going to be horizontal and going this way. I will say this, whenever they're perpendicular to the y, your equation inside of your integral has to be in terms of y. If they're perpendicular to the x, your equation has to be in terms of x, like we did for example 1. And your limits have to be consistent as well. So notice that our limits go from 0 to 4 this time for y. So our limits need to be in terms of y, our equation needs to be in terms of y, whereas before our limits went from -2 to 2 because they went this way, they were perpendicular to the x-axis. So everything has to be consistent as far as in terms of x and y. Step 5, label the dimensions of the perpendicular cross sections. So our cross sections that are popping out of the graph are going to look like this. It's going to have a certain height, and if you notice, the base of that cross section is actually going to be 2x. Let me explain why that is. Let's take a look at example at x equals 1. We know the y value is going to be 1 since it's x squared. The width of this particular triangle, the base of this triangle, is actually going to be 2. It'd be 1 going this way, but also 1 going this way. So the y value is 1, x squared, but the width of this is twice that, and that's going to happen all the way up through these cross sections. When we go to label the base of this triangle, we will make sure that half of the triangle is x this time. So that means that the height of this triangle, using a tangent function, remember the angle for an equilateral triangle is 60 degrees. So if tangent of 60 equals opposite over adjacent, h over x, we will end up with the height of this triangle being square root of 3 times x. Now, why are we labeling the dimensions of the perpendicular cross sections? Because when you're doing cross-sectional volume, you have to insert an area formula into your integral. Basically, you're finding infinitely many areas of these triangles to form this solid, which we're going to visualize here in just a second. Step 6 is to determine a formula for the area of the perpendicular cross sections. We know the area of a triangle is 1/2 base times height. So it'd be 1/2 times the base, which is 2x, like we said before, times the height, which is square root of 3 times x. When we simplify that, we get square root of 3 times x squared, which will give the area of one of these cross sections. Now, before I move on, I do want to take a look visually at what this will look like to give you a better conceptual understanding. So here is the graph of our function. We're going to be looking at a three-dimensional plane here, so we can see there are cross sections. This is our base of our solid, and this is y equals x squared. It's going to be going from 0 to 4. Let's just take a look and see what these cross sections look like as we move them. So we can see that as it goes from 0 to 4, the height of that equilateral triangle is going to increase because the width of this parabola increases. And so basically up into this point, we've determined the area formula for this triangle. So basically, to get the volume of this graph, you will just find the area of all of these triangles put together, and it will form a solid, which we will visualize once we compute the volume. So up into this point, we found the area of that blue equilateral triangle to be the square root of 3x squared. However, you will see in a second that this needs to be changed a little bit. Step 7, determine the limits of integration, the range of the perpendicular cross sections. Again, those triangles are be ranging from 0 to 4. You need that in order to set up your integral. Step 8 is to set up the integral. So it's going to be going from a to b. The volume is going to be equal to those limits from a to b of the integral of the area of the cross-sectional formula, which in this case, again, is square root of 3x squared. Now, here's where we need to make some adjustments. The limits in this case are from 0 to 4. Those are in terms of y. You can see that when we put a graph back up, it goes from 0 to 4. However, the equation that we have right now is in terms of x. The area of that blue triangle, we have square root of 3 times x squared. Now that is correct, but this can't be in terms of x, and while this is in terms of y. Remember, when your cross sections are perpendicular to the y-axis, as they are in this case, that means everything needs to be in terms of y, including your area formula. Fortunately, that's not going to be hard to convert. If we go back and look at our original equation, we can easily change this x to a y. Step 9 is going to be to determine a relationship between the variable of the integrand and the variable of the limits of integration. In short, what that means is if your limits are in terms of y, this has to be in terms of y. We're going to change that x to a y. Now that curve that we're looking at, that parabola, is y equals x squared. And so there is a relationship there. If y equals x squared, we can take the square root of both sides and get x equals the square root of y. And therefore, we can replace this x with the square root of y, which is exactly what we're going to do. Thankfully, that is convertible. Rarely you might run into a situation where you can't convert it. For example, if it was like y squared plus y, we can talk about that in another example though. Step 10 is going to use the relationship to write the variable of the integrand in terms of the variable of the limits of integration. So that x will become square root of y. You notice I did forget something here. Don't forget your dy. And that's because, again, these limits are in terms of y. So now that everything's in terms of y, we can go ahead and integrate. The definite integral, well, actually, square root of y squared is pretty cool, right? That just becomes y. So now we're just integrating square root of 3y dy. So we're just going to be using the reverse constant multiple rule. We can pull the square root of 3 out and then integrate y, which is just 1/2 y squared. We're going to be integrating from 4 to 0. Basically, all you have to do is plug in the 4. When you plug in the 0, it's just going to be 0, right? Just plug in the 4 here, square it. It's going to be 16 over 2, which is 8. 8 square root of 3 is going to be your answer. Okay, and that gives you the volume of that cross section. And that's it. That's your last step is, once you plug it in, that gives you the volume and you're done. So let's go ahead and visualize and see what this 8 square root of 3 is going to look like on our graph. All right, so here we have our function. Let's go ahead and just generate what this solid looks like by going ahead and hitting draw. Whoops, I forgot to put trace on. Give me 1 second. All right, let's try this one more time. All right, here is our shape being generated, our solid, with these triangles. You can see that the area of the shape changes. It gets bigger as we go along, and here is our volume down here. We end up with 13.86, which is equal to 8 times the square root of 3. And that will give us the volume of our cross-sectional solid generated from 0 to 4 between y equals x squared from 0 to 4. And if you look at it, basically, the left curve is x equals negative square root of y. On the right, we have x equals positive square root of y. Again, when you're integrating in terms of y, everything needs to be in terms of y. And as long as you ensure that, you will find the correct answer for the volume of your solid. For this example, if you have any other questions about it, let me know.